Okay, guys, this is our second lecture. We're going to consider today section 2.2, separable differential equations. Let's talk a little bit of what kind of equations are they? So we are going to consider first order differential equations looking like this. dy dx equals f of x, y. So dy dx is first derivative, so this equation is solved for the first derivative. Here can be any function of x, y. If our function of x, y can be represented as a product of two functions, separately function of x and function of y, what we can do with our equation is to represent it as m of x plus n of y dy dx equals to 0. Let's say how my f supposed to look if I want to do this. I think f of xy is supposed to look like m of x over n of y. So it's not necessarily supposed to be a fraction. It can be a product, like m of x multiplied by 1 of n of y. Important is that we can represent function f of x as a product of two functions. One depends on x, one depends on y. Now, if we can do this, we can obtain an equation like this. How? Well, just rewrite it. dy dx here, m of x, n of y, multiplying by n of y, we're going to have n of y dy dx equals m of x. We can move it to the other side. We are going to have a minus in front of m of x. It's not important, actually. We can call this minus m of x, and then there is going to be no minus in the final one. Important is that we can separate two parts of function f. If we can do it, the equation is called separable. Sometimes you are going to have separable equation looking like this also. So imagine that you multiply by dx both sides of this equation. Then you are going to have m of x dx plus n of y dy equals to 0. This equation looks even more symmetrical than the previous one, right? Basically, guys, if you can separate x's from y's as two terms or on different sides of your equal sign, the equation is called separable. Well, how do we solve separable equations? Let me first give you an example of separable equation, example of a solution, and then we can kind of validate why equation can be solved like this. Example, x squared 1 minus y squared. I'm just picking up the very simple example here, which is exactly like the fraction between m of x and n of y, right? The x function is on the top, y function is on the bottom. Equation is separable. And I'm going to separate variables. So all y's will go on the left side, all x on the right side. So I multiply the whole equation by 1 minus y squared over here dy. And on this side, I'm going to have x squared dx. So only y is here, only x is here. Well, logical step after that is to integrate both sides. Well, because this side depends only on y, this side depends only on x, I'm going to integrate them separately, like they are independent variables. They are not independent, but we are going to pretend that they are independent. I'm going to integrate them separately, so I don't know, I'm going to put next line 1 minus y squared dy supposed to be equal x squared dx, right? Everyone remembers how to integrate power function. So 1 is going to give us y, right? Y squared plus a constant c1, and here we are going to have x cubed over 3 plus a constant c2, right? Well, C1 and C2 are two arbitrary constants. What I'm going to do, guys, I'm going to put all variables on one side and constant on another side. Y minus y cubed over 3 minus x cubed over 3 equals C2 minus C1. I'm going to call this difference as a new constant C. What we got, actually, it's a very typical implicit solution. If you multiply the whole solution by 3, which is also a very nice way to kind of simplify it, we're going to get 3y minus y cubed minus x cubed. If you multiply constant by 3, it's going to become a 3 constants, right? But C is arbitrary constant. Means that 3 arbitrary constants is going to be just a new arbitrary constant. So I'm just going to write down C again. This C is equal to our old 3 C's. Okay? Implicit solution. Implicit solution. Why it's implicit? Well, because to solve it for y, you will need to solve cubic equation. Maybe you don't want to do it. So you're going to leave your solution like this. Okay, guys, one thing I did not do here, I did not check what happens to this one when I multiply by it. Remember that actually for equation like this, we cannot have 0 in denominator, which means that y is not equal to what? Plus minus 1. When I multiply by it, basically my equation allows me to set up y equals plus minus 1. Nothing is going to be bad, right? 1 here, 1 here. There's going to be a certain x depending on the constant. So you will need to set up this separately as addition to the solution, because actually your original equation is not allowing y to be equal neither 1 or minus 1. Okay, let's consider another example of differential equation and separate variables. Example 2, that was example 1. Let's make example 1, example 2. Well, again, mostly you are going to recognize separable equation, because on the right side you are going to have something like a fraction or something which can be turned into fraction. We're considering initial value problem. Besides equation itself, we do have initial value given. So y of 0 equals to -1. What we have over here is first order differential equation, right? And we have initial value problem. I'm going to label it somewhere. Initial value problem. Which means that my final solution is going to have no constants like this one. This one was not initial value problem. Well, easy to separate variables, right? I'm just going to move my denominator over here, remembering that y is not equal to 1. I'm going to set up somewhere y is not equal to 1 and move my denominator here to y minus 1 dy. Dx will go this side. Dx. And integrate both sides, right? Let's put integral. Integral here. Should not put parentheses here. Okay, dx. Now I'm just going to integrate 2y dy is going to give me what? Y square. It's supposed to give me 2y square over 2, but I'm dividing by 2 and 2, canceling them, right? Minus 2y plus constant 1, and here 3x cubed over 3. I'm going to write it down, 3x cubed over 3 plus 4x squared over 2, power function integration, 2x plus c2, right? And what I'm going to do, I think I'm going to move everything on one side and constant on another side. So I'm having y squared minus 2y. Here 3 and 3 cancels, so minus x cubed minus 2x squared cancels, minus 2x equals, and these constants unified together are going to give me constant c. C constant, right? Now guys, remember that this solution is first implicit. Implicit means that I'm not solving separately like for y here, which I can do this, but I'm not doing it right now. Besides that, I have initial condition, which is going to find for me what is this constant, because when it's a constant, it's going to give me a family of curves. Like, remember, like we can have family of circles, concentric circles, for example, sitting around each other. Here, if we find C, that's going to give us one circle. Well, that's not exactly a circle, but like one curve. How do we find C? I'm going to plug in 0 instead of x and -1 instead of y. So I'm going to put x equals 0 and y equals -1 into my equation to find a constant. So -1 squared is 1. -1 by -2 is 2. 0, 0, 0, all zeros equals a constant. So very easy, my constant equals 3. Let me write down the final solution. I don't know. Can you see it below here? I'm going to move it a little bit up. So I have y squared minus 2y minus x cubed minus 2x squared minus 2x, sorry, equals 3. That's my final solution. Let me check if I have to mention that y is not equal to 1. What is going to happen here when y is equal to 1? Well, I'm going to exclude certain x's, right? If y is equal to 1, I'm going to have 1 minus 2, which is -1, and that's going to give me a cubic equation. Well, I'm just going to add that y is not equal to 1. I'm going to solve cubic equation. Here for x, I'm going to get a cubic equation, which, let's say, I don't know how to solve right now. Or you can always look up general solution of cubic equation online and find out which x's are not going to be used for this equation. Let me double check it before I move to the next problem. Well, everything looks fine to me. I'm thinking if I can solve for x without actually doing cubic equation. Probably I can, but I don't know yet. Okay, I'll think about this. Maybe at the end of the lecture I will do it. So let's move to the next example. Example number 3. Let me see that we can everything fits into our video field. Next example, dy dx equals y plus 1 sine of x. Well, looks like a product. We can separate it, right? I'm going to divide by y plus 1. So I'm going to have dy over y plus 1 here. And here sine of x multiplied by dx. I'm supposed to remember that y plus 1 is not supposed to be equal to 0. Because when I'm dividing it, I'm kind of forgetting about it, right? I'm kind of dividing and don't want to have 0 here. What is going to happen if y equals, actually y plus 1 equals to 0? Well, is it going to be a solution? Because this one allows us to have y equals to -1. This one does not allow. So this one is not going to have it as a solution, but this one probably is going to have it as a solution. Is it a solution actually? Y equals -1. Let's check. So y equals -1. Is it going to, it's just a constant, right? Is it going to work here? Well, what is derivative of -1? Plug it into equation. Derivative of -1 derivative is 0 equals -1 plus 1 multiplied by sine of x. Well, that's 0 by sine is 0, and I'm going to get a true statement. So actually, this is a solution, which I'm going to lose when I move to this next step, just because I'm not allowing anymore y be equal to -1, but I'm going to remember about this solution, okay? Now I'm just going to do integration. Integral dy y plus 1 equals integral of sine of x dx, and that's going to give me what? ln of y plus 1, right? Here, the integral of sine is cosine of x, and with minus. I'm not going to write down two constants anymore. I'm just going to combine them together into one constant. Actually, each side is going to produce a constant, but I'm going to combine it into one constant. Now, guys, this one, I want to have an explicit solution. To show you one little trick which we do with constants. To get explicit solution here, we got implicit solution. It's not initial value problem, so actually we are fine already. But I want to show you one little trick And to show it, I need to do explicit solution. To do explicit solution, I need to solve it for y. Step number 1 is to raise e to the power of both sides, right? To eliminate a ln. Remember cancellation rule. E and ln are inverses. We cancel them, so we have here y plus 1 absolute value, and here e to the power of negative cosine of x plus a constant. Now, I'm going to show you my trick, and then we are going to finish solution. What I'm going to do is this. I'm going to represent it as a product. Why? Well, guys, remember that if you do have a same base, you just add powers, right? So now what I did, instead of adding powers, you can imagine that you add these two powers, get this one, or you can go back, separate the powers, right? You know that c is arbitrary constant. When you raise e 2.7 something into the power of arbitrary constant, you are going to get arbitrary number. So you can make this one as a new constant. The only condition on this new constant is going to be that this constant is greater than 0, because exponential function is never less than 0. Remember how it looks like? It looks like this. Exponential function, always greater than 0, right? Okay, good. So what I'm going to get, y plus 1, I'm going to put this my new constant c, e to the power of negative cosine of x. Now I'll need to open this absolute value. I do remember that. How do we open absolute value? Well, when expression under absolute value is positive, then it's just equal to this. So let's consider that it's positive. So let's imagine that y plus 1 is positive. And we are just going to have this, right? Y plus 1 greater than 0. When expression is positive, we are going to have this expression. And it's going to give us a solution looking like this. Y equals ce minus cosine of x minus 1, right? Very good. When expression is negative. So if it's negative, then absolute value is going to take away the minus, right? So just like if it was minus 5, absolute value is going to put like extra minus in front of minus 5, turn it into 5, and then give you the final solution. I'm going to do same. I'm going to put minus. So this minus for negative expression is going to work like absolute value. And I'm going to have c e to the power of negative cosine of x, which is going to give me, opening this, minus y minus 1 equals c to the power of negative cosine of x, or y equals, if I multiply everything by negative 1, is going to be negative c e to the power of negative cosine of x minus 1. Sorry. Let's look at these two solutions. So again, what is here? Y plus 1 is less than 0. Y plus 1 is less than 0. I'm opening absolute value. 1 and 2. If you compare two final solutions, this one and this one, between each other, you're going to see they're exactly the same, with one little exception. Here we have minus, here we have plus. But remember that my constant c was only positive. So if I have minus in front of positive constant, I'm going to get arbitrary negative number. So if I allow my constant to be positive and negative, I can unify these two expressions into one. I can write them down like this. C e to the power of negative cosine of x minus 1. And my constant is any number. Not necessarily positive like over here. Right? The only one thing is missing here. I forgot about solution y equals negative 1. So far, guys, my constant can be negative, can be positive, but cannot be equal to 0. Exponential function, no matter positive or negative, is always like a number. So can my constant c be equal to 0? Because right now, c is any number, like greater than 0, c is less. Sorry, my pen is running out of ink. Okay, little interruption. So, as I said, my constant here so far can be only positive or negative. It cannot be equal to 0 because exponential function always going to give you a number. Can it be equal to 0? Let's look at this solution y equals negative 1, which we kind of separated from everything in the beginning because we were dividing by this. is it going to be included here? Well, if c is any number, positive or negative, but not 0, this solution is never going to be represented here because it's -1 plus something. But if we allow c to be equal to 0, we can include solution y equals -1, because when c is equal to 0, y equals -1. So actually my solution is going to look very, very simple. It's going to be c to the power of negative cosine of x minus 1. And here I'm going to allow c to be real any number, not just greater than 0, less than 0, or just greater than 0. C is arbitrary constant. Okay. Visible? Visible. Very good. Well, guys, I was using this example to show you what manipulations we can do with a constant. Why do we need to know them? Is it going to be okay to leave your answer like this? Yeah, guys, it's going to be okay to leave your answer like this. Like this. ln equals to cosine plus a constant. But when you compare your solution of homework with a book solution, they will do all these manipulations. And when your solution is not going to match theirs, it's not because it's wrong. Probably it's right, but they manipulated with a constant a little bit and they moved it to most simplified form. You will supposed to be aware about this, right? About this manipulation like e to the power of constant, about considering positive and negative constants and 0 constant if solution is included. Okay, now guys, what I want you to do, I want you to solve a couple of problems by your own. They are book problems. So, problem A, xy prime equals 1 minus y squared to the power of 1 over 2. And problem B, y prime equals 1 minus 2x over y, initial condition y of 1 equals -2. This is general problem, this is initial value problem, and you can spend like 5-10 minutes on solving these two problems. I'm going to solve them too, but I want you to try first, like how far you can go by yourself, okay? So I'm going to count to 3, and during this counting you can stop your video and then try to do the problems and then restart your video and see how solutions are going to look. So 1, 2, 3 solutions. I'm going to start with problem A. So xy prime equals 1 minus y squared. Well, maybe I should write down instead of 1/2 a square root, right? It's going to be more like general for us. Now, separation of variables is going to give me what? Dy over a square root of 1 minus y squared equals dx over x, right? X moves to the right, the square root moves to the left, both are coming into denominator, and y prime is dy over dx. Well, now I'm just going to integrate. I'm going to remember that when I divide by something, I'm going to exclude two solutions. So y plus minus 1 is going to be excluded from this one. What are we going to do at the end? We're just going to check it, but not right now. Right now, let's solve it and then check if it's going to be a solution. So, maybe guys, you still remember that integral of this expression is what? Arctangent. Well, not arctangent, that's sine actually, sorry. So, maybe I should write down the integral first. And then kind of do the answer. So I'm going to write down sine inverse of y, right? Remember, it's just a stable integral. This one is what? That's ln of absolute value of x, and I'm going to put a constant here. Well, basically, guys, we are done. If you wish to solve it for x or for y, you can do it. But in this case, it's not going to make anything good out of it, because well, you take a sine of both sides, that's going to give you a sine of ln plus a constant, which is not going to look much better than this one. But, well, again, if you take a sine from both left side and right side, you are going to find y explicitly. I was thinking to now check back if y plus minus 1 is a solution. How do we usually check it? You just literally substitute it into your equation. So remember that derivative of a constant, either 1 or -1, derivative is going to be 0. So here we do have 0. Derivative of a constant is 0. What is going to be here if I plug in the numbers? Well, I'm going to get 0 too, because it's 1 minus 1, because both of them are going to be squared and give you 1. So we have 0 equals a square root of 0, so they are solutions. Well, what we should do with the solutions, we're supposed to add them somewhere here, because this expression most likely is not going to include them. So write down that y also equals plus minus 1. That's a solution. Second problem, problem B. Well, again, we are going to do separation of variables. I'm going to write it down like y dy, y moves over here and here, 1 minus 2x dx, right? Well, we know that y, which we get from final solution, not supposed to be equal to 0. Let's hope that it's not going to happen actually, but who knows. So I'm going to integrate. I'm going to get y squared over 2, right, from this one, equals x minus 2x squared over 2 plus a constant. I think what I'm going to do, I'm going to plug in my initial conditions here to find the constant, okay? So let's first write them down. X equals what? 1, y equals -2. I'm going to plug into my final solution. So -2 squared is 4 over 2 equals 1 minus this 2 and 2 cancels, and this is what 1 squared is 1 plus a constant. So this is 0 and this is 2, so my constant equals 2 actually, right? Well, let's put it back into equation. Y squared. I'm going to actually maybe multiply everything by 2. You know, multiply this side by 2, this side by 2, equals 2x minus 4x. Oh, no, 2x, because we canceled 2x squared, plus 4. This one is 4, right? Because it was constant, equals 2 multiplied by 2 is 4. I want to find y, so I want to solve it explicitly. Remember, when you extract the square root, you are going to have plus minus in front of the square root. So which one should I choose? Actually, I got 2 solutions, right? Remember uniqueness question we had in the previous lecture. So how do I figure out which one should I use? I'm going to look at my initial conditions. My initial conditions either here or here is that y of 1 equals -2. So I'm going to plug in 1 here. 1, 1. I'm going to get 2 minus 2 square root of 4. Square root of 4 is supposed to be equal -2. Well, I can get -2 here only one way, using the minus. So I'm going to choose the minus. Initial conditions. So my final answer is minus square root of 2x minus 2x squared plus 4. If I do it explicitly. Okay, so we're done with this problem. Sometimes it's going to be a good idea to check on which interval solution is going to exist. You see that we are dealing with a square root here, right? The values under the square root or square root itself is going to work only when the values is positive or equal to 0. And in our case, it's not going to be always, right? It's a parabola. Parabolas sometimes are greater than 0, sometimes are less than 0. I'm going to find out where this expression is greater or equal to 0 to find out for which x I am going to have a solution. Because if something under the square root is negative, I'm not going to have a solution. And it does not matter that I solved it for y. If I did not solve it for y and I have negative number here, I'm not going to have it as a solution, because you understand that negative number here will never be equal a square of something, because square is always positive. What I'm going to do, guys, I'm going to just find out 2x minus 2x squared plus 4 equals to 0. I'm just going to use a test points method. So I'm going to find solutions of this equation. And there x equals, I think, minus 1 and 2. Let me check it. Well, it's quadratic equation. You know that you can use a formula or you can use whatever. I'm going to show the formula. Plus minus square root. If we cancel 2, 2, and 2 here, we're going to have 1, 1, and 2 here. So we're going to have b equals 1 minus plus 4, 2, minus 1 over 2 by negative 1, which is going to give me plus minus 3 minus 1, 2 over minus 2 minus 1, or minus 3 minus 1 minus 4 over minus 2 minus 2. Two solutions. So that's minus 1, that's 2. This parabola goes like this, right? So positive interval sits between the points. We can allow the expression be equal to 0 because the square root of 0 is 0. So we are okay with 0, right? The only thing we are not okay is to have 0 as y, right? Remember that just like if we plug in minus 1 here, we are going to have 0 here, and y is going to be equal to 0, which is not allowed by the original equation. That's why I put the circles. So my solution is from negative 1 to 2. Well, again, why do I exclude endpoints? Not because we cannot extract the square root of 0. We can extract the square root of 0 perfectly. But when expression under the square root is equal to 0, then y will be equal to 0. And we do know that y is not equal to 0. Well, I did not mention it anywhere, but I'm going to write down y is not equal to 0. When we multiply by y, we include y equals to 0, but actually original one does not include it. Okay. Well, now, last question left is why actually we can do this integration. I have a little space over here where I want to discuss a little bit why we can do separation and then integrate left side and right side. Is it going to give us correct solution? I'm going to box a little space over here and try to justify it. Well, imagine that we represent our equation as h of y dy dx equals g of x with separate variables, but we did not move dx on this side yet. I did it on purpose. If you do integration of this side and this side, that's going to give you exactly what we have over here. Even if you don't move dx here, when you integrate g, you kind of understand that you integrate g dx, right? Imagine that h of y is a derivative of some antiderivative h of y, and the g of x is a derivative of some big g of x. Well, these are antiderivatives, these are derivatives, right? So what we have actually, we have h prime of y dy dx, and here g prime of x. Well, again, when we do integration, we are finding antiderivatives. Basically, these g and h are antiderivatives. Like in this case, it's a sine inverse and a ln, right? If you differentiate them, you're going to get 1 over x and 1 over square root. Now, guys, if you look at this expression, you're going to see that h of y, kind of independent function, but then you multiply it by derivative y dx. Remember how we differentiate composition? We actually differentiate it like we differentiate outer function, like it depends only on like y and y is independent. And then we differentiate the inner variable, like y of x. So actually here we have a derivative of y of x. If you differentiate it by x, I'm going to write it like this, d dx h of y of x. How would it look? You differentiate it by x. You differentiate first h as function of y, like over here, h prime, and then you differentiate y, dy dx. So that's exactly what we have. What is this? Well, this is dg dx, right? I'm going to write down dg dx. Now, we do have two derivatives equal. Derivatives are equal when the functions which were differentiated are equal or different by a constant. For example, you differentiate x squared, right? And derivative is 2x. And you differentiate x squared plus 2, and derivative is 2x2. Two functions are going to give you same derivatives only when they are different by a constant, which means that h of y of x is equal g of x plus a constant. Well, you can write down the difference between them equals to a constant. Well, that's exactly what we have when we integrate, right? We integrate something, we calculate the function h of y. On this side, that was sine of inverse, right? And then we calculate g of x, antiderivative of 1 over x, like, and then a constant. So that's exactly what we are doing. So that's just justification of the method of separation of variables. Okay, I think we kind of done with separation of variables. Do your homework, and don't forget, if you divide by something, remember that you either are going to lose a solution. If you multiply by something, you are going to add a solution. So check back if you did not like add something what is wrong. Okay, that's all.